try to look straight up and not through the air, right? But sometimes you can't avoid it. So we have all these measurements that we throw out. Using this method, we can actually make interesting calculations with crappy measurements that are useful. Okay? So, let's see. So what we look at is the positional offsets that's caused by something called differential chromatic refraction. So the air in the sky is refracting that light down, and we get a position for the object in blue, red, green, etc., etc. Okay? And the offset is different in each of our different filters. So this is really overwhelming, but just look at one of them. So these are the different filters that I showed you before. Right? Here's our ultraviolet, here's our blue, here's our red, here's our near infrared, and here is the infrared. And this is your normal spectrum of your quasar. Now, we have built into all of the computerized stuff with the telescope to automatically correct for the offset for a typical star. But they didn't correct for the different kinds of objects. And when you get these funny peaks from the quasars in each of the bands, you change the effective wavelength of that band. So a star that has a flat spectrum through here bends at a certain amount in each of these bands, and it's automatically corrected for. By having this funny little peak here, when the telescope looks at it, it sees it at a different wavelength in general, and it changes the position that the atmosphere refracts that object to. So, in this diagram here, where the telescope is seeing the object here, if it's a quasar, it looks to be here instead. It changes the position that the object is observed at by the telescope, which you never would have thought about, so there you go. And it depends as well on how far away the quasar is. Remember I said that an object being further and further away shifts it into the more red light. So it also moves these peaks into different bands. And so the position of the object in the sky changes depending on how far away it is. Okay? So here's kind of what that looks like. So here is how much difference it makes in the U band, in the ultraviolet, and how much difference it makes in the green. And these are everything that's not quasars, so stars and galaxies. And so there's a little bit of dispersion here in the green light and a little bit of dispersion here in the U. And some of that's from noise, some of that's from having a variety of objects. But here's just the quasars. And you can see there's a much bigger dispersion in the U band. And we can incorporate that into the classification. We can say the U slope versus the G slope for stars and for quasars, and add that into the four-dimensional selection to include that in the classification. And this is actually working great and helping with the accuracy of the classification. Okay. Does that make sense? Any questions? Okay. That's all I have for now.
Great. Thank you. Time for some questions?
Oh, what is stochastic?
Random,
Oh,
basically.
that's okay.
So, yeah. Yes.
Well, it's just
What is something that's further away redshift?
Oh, that's a loaded question. I could talk about that for a while. So, you've heard that the universe is expanding, right? Okay, so...
Is it simply Doppler effect?
Yes, yeah.
Okay.
It's Doppler effect, but with light. So an object that's moving away from you, the light gets spread out as it's moving away, and so that makes it a longer wavelength, which is more red. So if it's optical, that makes it more red. If it's already in the infrared, that just makes it more and more infrared.
Doesn't that mean that we have to say it's more redshift? It means we assume that it's moving faster.
Mm-hmm.
Do
And it
we-
also has more space for people to spread out. But
Do we have a way to confirm that it's indeed moving faster rather than, oh, it's not really redshifted at all?
yeah, they've done a lot of stuff with certain kinds of supernovae to do that. That it is, yeah.
Oh,
Yeah. I can tell you more why, but yes,
oh, you'll
it
lose me
has.
so quick. It's not-
Yes.
So how do you get the data from the 17,000 objects?
So I use a database from the Sloan Digital Sky Survey, the one with the filters I'm looking at, and actually all of that data is completely open to the public. So anyone can go in and dig through it and grab what they like. So it's just on their servers. I can give you the link if you want to look. They have pictures of all the objects too on there, as well as the like the breakdown of the colors after they've processed the images.
I'm just a biologist, but I have a brother who's an astrophysicist. And there's a question I've wanted to ask him, except I think he'd probably laugh at me, about sort of quasars. And so I don't know if I've watched too much science fiction or if these even really exist, but is a white hole related to a quasar? Are white holes even real? That spew out matter? Or is
They're
that,
not related to quasars.
are they real things?
We haven't seen any.
So they're more theoretical.
If you ask a string theorist or somebody, they might tell you yes, but I would say no. Yeah. We haven't actually seen any.
Are there specific questions about the early universe that are going to be answered by information from quasars?
Yes, so looking at quasars, you can see that it is generally accepted that quasars were much more common a long time ago. So one thing we look at with them is how much more common it was to have galaxies colliding. So if we look towards the center of our Milky Way, we don't see anything spewing out and making tons of light. It looks completely dark. But quasars seem much more common looking back. And looking at that, it seems like it was much more common for galaxies to collide and cause these nuclei to become active by having all that gas and dust start to fall in. And so you can kind of see how much more closely together and smaller all the galaxies were. But you can also look at just the general distribution of stuff in the universe at that time. So we can't see anything except for these quasars, but by looking at them we can kind of map out where the matter was at early times, which is kind of interesting to kind of help piece together theories about how the universe got to be the way it is now. So those are some of the big questions.
With that, the distribution of matter, like how would one use the distribution of matter to decide anything about the early universe, I guess? Like, other than what the distribution was?
Oh, so, several things. So, like, they're piecing together bits of information along the way. And by having information about how dense it was in a certain spot or another spot, then you can rule out certain theories. So it doesn't give you the whole picture, but it helps to confirm, like, what cohesive theories you have about the evolution of the universe, which ones could possibly be right, and kind of help to piece together the big picture. So you don't get a big picture from looking at the quasars at that time, but they are the best information we have about that part of the evolution of the universe. Did I answer your question?
Yeah.
Well, I'm sure Tina would be glad to take more questions, any of you want to come around, but let's thank Tina one more time.
Thanks very much.